Questions about what we just finished. Regulation of extracellular fluid volume by the kidney. No questions? Okay, inshallah we'll start today. We'll take it easy with acid-base balance. Remember, this is another one of these functions of the kidney. Regulates our hydrogen ion, and this is referred to as acid-base balance. Now you've heard that our pH is 7.4, right, under normal circumstances. So we will try to understand what's the point of that and how do we keep it regulated at that number, which is 7.4. Yes, you have questions?
Oh no, they were just putting press up on my arm.
And functions of the kidney is really to regulate our acid base in our body. Now, some of the areas we will take it easy. I know this is, I have noticed, since I've been teaching for a long time, it seems like students have a hard time understanding acid base regulation, so we will try to make it as easy as possible, within reason. Let's remember, it has a lot of chemistry, and chemistry is not my area of, I don't like it very much, but I know enough to teach you what you need to learn about this. So we will try to define what are acids and bases, and remember we do have acids or bases in our body, and they play a role in the regulation of our pH. We will see, how is hydrogen ion regulated. Remember, some of the substances that we said are tightly regulated so far was sodium, potassium, calcium. We said phosphate, it's not important, it can go up and down. So there are some substances that are very tightly regulated in our body, and usually there is a good reason for that. One of them is hydrogen ion. So we will see what are the different mechanisms that prevent hydrogen ion from increasing too much or decreasing too much in our bodies. Then there are three main systems that help me regulate acid-base balance. One of them is the body fluid buffers. Inshallah, we'll talk about those today. The second is the respiratory system, and we talked about this, but we will mention it briefly. Remember, we said the number one, remember the central chemoreceptors? They are stimulated mainly by what? By carbon dioxide, PCO2, right, in the arterial blood. But they're, the direct stimulus for these chemosensitive areas is the increase in H+, okay, which is kind of similar. Increase in PCO2 is similar to an increase in H+, and we will see how that works. So therefore, these body fluids, they're practically the first line of defense against changes in hydrogen ion. If they fail to fix the problem, my respiratory system is the next one. And you know what happens if I have a lot of PCO2, which means a lot of H+, what is the respiratory response to that?
Increase
Hyperventilation? Hyperventilation, so I blow off a lot of the CO2 that will reduce H+ concentration in my plasma. The third line of defense, which takes a couple of days to develop, is really the renal mechanisms. And the nice thing about the renal mechanisms is that, well, we can say that also about the respiratory mechanisms to some extent, but the renal mechanisms for controlling hydrogen ion can be regulated. And we will find out, inshallah, by the end of these lectures on acid-base regulation of how does the kidney regulate hydrogen ion as well as bicarbonate ion reabsorption. Okay, so we will look at what happens, how do I buffer hydrogen, how do the body fluids buffer hydrogen. Then we'll talk about the bicarbonate buffer system, which is very important in terms of the body fluids. Phosphate buffer system. And we mentioned that in the past, a long time ago, and we said phosphate usually in my plasma, you can find it in two forms, HPO4 or H2PO4. Or if you remember, I said how much am I going to have of HPO4 versus H2PO4 depends upon the pH, and we will go over that again. Then we will switch to the respiratory regulation of acid-base balance, and again that happens as a result of the PCO2 in my arterial blood that determines the respiratory rate. And of course, high levels of PCO2, as we've seen, can stimulate ventilation, so you hyperventilate, and that results in you get rid of a lot of CO2 that usually helps me regulate acid-base balance. Then at the end, we will talk about the renal control of acid-base balance, and that usually occurs as a result of regulation of H plus and bicarbonate. Again, this is the renal mechanisms are quite effective, they can be regulated, and we'll see how that happens, inshallah, by the end of these lectures. Then we will go over some clinical problems that might occur. And believe me, no matter what field you go into, you will end up with patients who have acid-base imbalance. So you really need to treat them, and in order to treat them, you need to understand the problem to begin with. Okay? And of course, that requires some understanding of the renal function. I know very often you're going to have problems that might have something to do with the fact that they have renal failure or they have kidney problems. Okay, so what is the objective of acid-base regulation? Well, the objective is really to maintain a normal H plus concentration in our body fluids. Remember, this extracellular fluid volume that we talk about, that's where all the cells are bathing, that's where they're living. This is the internal environment for these cells. So therefore, and we said that's homeostasis really, in order for us to maintain constant constituents in the extracellular fluid compartment. In fact, that is a reflection of whether these cells are going to be healthy or not. And they do not like any changes in the extracellular fluid volume or constituents. So how do you maintain normal, quote, normal H plus in the fluids? You do that because we do have extracellular or intracellular fluid buffers that allow me to neutralize H plus when I need to. The second line of defense would be the respiratory system. And if I have an increase in H plus, usually that's an increase in CO2. So therefore that can stimulate or inhibit depending upon how much PCO2 I have or how much CO2 I have. So therefore my respiratory system can participate in controlling the amount of H plus or maintaining a normal H plus in my body fluids. The kidney participates in acid-base balance by doing what? It reabsorbs bicarbonate. This is its first role. Second, it secretes H plus. Remember, we have already seen we have already mentioned few things about H plus. We said, we have sodium hydrogen exchange, and you see that that's in the proximal tubule with distal tubule, thick ascending limb of Henle's loop. We have this luminal transporter, which we call sodium hydrogen exchanger. I reabsorb sodium and I secrete a hydrogen. Then we talked about the intercalated cells. We said these can secrete hydrogen ion against a concentration gradient of 1 to 1,000. So they can be very effective in allowing me to get rid of a lot of H plus. I know I almost reabsorb all the bicarbonate that I filter. I can neutralize H plus with bicarbonate. Not only that, but the kidney can even synthesize bicarbonate. Has nothing to do with the bicarbonate that you filter. It will synthesize new bicarbonate. Now, when do you think I'm going to need to synthesize more bicarbonate? When I have acidosis or alkalosis? Acidosis, then I need more bicarbonate to neutralize the H plus. So we will end up with this main function of the kidney, which is regulation of acid-base balance. And in short, if I want to summarize that, the kidney regulates acid-base by reabsorbing bicarbonate with secreting hydrogen ion. Now, how much do I reabsorb or how much do I secrete? That's the whole process of regulation. Okay, some definitions, you might know this stuff. That's okay. Yes, ma'am. You will not have what? You will not have alkalosis. You will have alkalosis if you have lower levels of H+. Yes, under normal circumstances, you don't have alkalosis. You don't have acidosis. But if something goes wrong, you will have alkalosis or acidosis. One of them. Okay. So remember, we will talk about normal regulation, which under normal circumstances, you don't have an acid-base problem. So your kidney, your respiratory system, your body fluids are regulating your acid-base balance. You have no problem, but we want to talk about clinical situations where there is a problem. Okay, some of these definitions you know, but we want to at least go over them for the people who don't know. And again, I sympathize with people who don't know a lot of chemistry because I'm one of them. Okay, so hydrogen ion, this is a single free proton that is released from a hydrogen atom, H+, that's it. An acid, again, it's a molecule that contains hydrogen atoms and can be released as H+ in solution. That's the definition of an acid. Acidemia, what is acidemia? This is an increase in H+ concentration in the blood, which means a decrease in pH. And that's usually caused by a pathophysiologic process called acidosis. And what is acidosis? It's excess H+ in my body fluids. A base, what is a base? This is an ion or a molecule that can accept an H+. Okay? Now, for example, bicarbonate, that can be considered a base because it can combine with H+ to give me carbonic acid, which is a weak acid. Alkalemia, what is alkalemia? This is a decrease in H+, concentration in the blood. Of course, it results in an increase in pH, and there's an inverse relationship between pH and the concentration of H+. And this increase in pH is usually caused by a pathophysiologic process that is called alkalosis. Excess removal of H+ from the body. And remember, one example we gave of alkalosis, we said if a person has Conn's syndrome, remember, they have a lot of aldosterone, are they going to lose a lot of hydrogen ion? Yes, and these patients will have alkalosis. Okay, so we gave an example already of that. So that's not normal regulation. These people have a clinical problem, which is called alkalosis. Then they're losing a lot of H+, so therefore their pH isn't going to be up or down. Up, it will be up. Okay, now strong acids. What is a strong acid? Strong or weak or what? Okay, an acid that rapidly dissociates and releases large amounts of H+. If you have an acid that does that quickly and releases a lot of H+, we consider that a strong acid. An example of that is HCl, hydrochloric acid, and of course we have a lot of that in the kidney. Weak acids, they have less tendency to dissociate and they release therefore H+ with less vigor. They don't release a lot of H+, they don't have the tendency to dissociate. And an example of that is carbonic acid, H2CO3. So it is a weak acid, while hydrochloric acid is a strong acid. It releases a lot of H+, and it dissociates very quickly. Strong base, what is a strong base? This is a base that reacts quickly and strongly with an H+, and therefore can quickly remove H+ from the body fluids. An example of that is hydroxyl ion. Hydroxyl ion, OH, can react very strongly with H+ to give me water. So it kind of neutralizes the H+ and solves my problem. A typical weak base is again bicarbonate. Bicarbonate is a weak base because it binds with H+, it can do that, but it binds with H+, much more weakly than does hydroxyl ion. Again, hydroxyl ion, we consider that a strong base. Now, again, as with sodium or potassium or calcium, we said that these substances are regulated very precisely in the kidney, in the body fluids, because we know our bodies don't function properly if you have an increase in potassium or a decrease in potassium. We saw what happens to your heart, to action potential, all that. And now H plus regulation is essential even more. And H plus is regulated even more strongly than these substances we talked about, and we said they are regulated quite well. The reason for that is because, remember, we have so many chemical reactions in our body, and all of these chemical reactions are affected by the pH. So therefore, it is critical to have an H plus concentration that is appropriate for these chemical reactions to occur. We already mentioned a couple of things. We said if I have acidosis, which means an increase in H plus, right? We said the sodium-potassium ATPase is inhibited, doesn't work very well. There are so many other reactions that are affected if you have an increase or decrease in H plus. The normal concentration of H plus in the extracellular fluid averages, look at this, 0, 4 zeros and 4 milliequivalents per liter. Now, what was the concentration of sodium in the plasma? 140 milliequivalents per liter. This is 0.00004 milliequivalents per liter. And the concentration is like 1 over 3.5 millionth of sodium. Okay, so it's extremely low. The normal variation in H plus, remember, now sodium is really nicely regulated. It's 142 or 140 milliequivalents per liter, and it goes up probably to 145, 138, and we said that's fantastic, it's regulated so nicely. Well, look at hydrogen ion. Normal variation in concentration of extracellular fluid of H plus is about 1 millionth as great as the normal variation in sodium concentration. Yani, we thought sodium varies is really, very tightly regulated. This is even more tightly regulated. It changes like 1 millionth of the changes in sodium. And again, the reason for that is because all these chemical reactions that we have in our bodies require a very specific pH. So therefore, it is absolutely critical to control the concentration of H plus in our bodies. Yes? So the concentration of hydrogen ion, the variation in it is like 1 millionth of the variation that you find for sodium. Again, which tells you how tightly regulated it is. And it's very easy to understand why is it that tightly regulated, because all these chemical reactions that exist in our body require a certain pH, and therefore, the pH of 7.4 seems to be most appropriate for that. The normal H plus concentration again is 40 nanoequivalents per liter, or 0.00004 milliequivalents per liter. If you change that to equivalents per liter, it's 7 zeros and 4. Okay. Now the pH is defined as log of 1 over the concentration of H plus, which is equal to minus log of the concentration of H plus. Therefore, the normal pH, and we know the concentration of H plus, it's this much. So minus log of this is equal to 7.4. This is the log to the base 10. Okay. So you probably understand now how we get this 7.4. Well, now the pH of the arterial blood is 7.4, whereas the pH of the venous blood is about, interstitial fluid is about 7.35. Remember, the venous blood has more CO2 in it. So therefore, the pH is a little bit lower than 7.4, so it's 7.35. يعني طبعا. Again, remember the variation in H plus is in the plasma is extremely low. Yeah, Shabab, you have a question? Okay, so now your pH is 7.4. Yeah, Malim, you have a question? Now, a person can live for a short period of time, very short period of time, and don't let that happen. If your pH goes down to 6.8 from 7.4, or if it goes up to 8. So you have like plus or minus يعني 0.6, that's it. And these are the limits for your life. Okay, so there are, as we mentioned, 3 primary systems that help me regulate the H plus in my fluid, in my body fluid. These are the chemical acid-base buffers that we have in the body fluids themselves. And these are kind of the first line of defense. So we do have some, some of these buffers combined right away with H plus to neutralize it if it goes up. And then I have the respiratory center, which is regulated, well, stimulated by PCO2. So therefore H2CO3, and we will find out if I have more CO2 in my blood, that translates into H2CO3. And therefore, my respiratory center, if I increase ventilation, I can excrete, well, I lose a lot of CO2, and that can regulate my hydrogen ion. The kidney can excrete either an acid or an alkaline urine, so therefore it can readjust the concentration of H plus in my fluid, and of course it can excrete urine with a lot of H plus or a little bit lower H plus, and again it can play around with the reabsorption of bicarbonate to buffer all that. Okay, well, now let's have some definitions, because they will help us a little bit understand the normal regulation of acid base. We have something called metabolic acidosis. Metabolic acidosis. The minute you see metabolic, the problem is with bicarbonate. Okay? Keep that in mind. The minute I see metabolic, my problem is with bicarbonate. And in this case, my bicarbonate is lower than normal. So you can imagine, if I have lower bicarbonate, am I going to neutralize a lot of the H plus?
No.
No, so do you think I will have more H plus?
Yes.
Yes, that's a problem, and it's called acidosis, right? The minute I see metabolic, I know the problem is with bicarbonate, and the minute I see acidosis, I know the pH is low. We know both of these things. Sure enough, what happens with these people? The pH will be lower, bicarbonate will be lower, and their respiratory response for this, or my respiratory compensation for that, will be hyperventilation. That will reduce my PCO2. Let's leave the compensation till later. Okay? I have metabolic alkalosis. The minute I see metabolic, where is the problem? Bicarbonate. And alkalosis, that means high pH, right?
Yes.
High pH, so therefore my bicarbonate is large. My pH is large, my bicarbonate is large, and the respiratory response is an increase in PCO2. Does that mean hypoventilation or hyperventilation? Hypoventilation. Respiratory acidosis. The minute I see respiratory, the problem is with the CO2. Okay? The minute I see metabolic, the problem is bicarbonate. The minute I see respiratory, the problem is with PCO2. Respiratory acidosis. Does that mean I have high pH or a low pH? Low pH. Why do I have low pH? Because I have a lot of CO2 or a lot of H plus. And my response, my renal response for that is increased bicarbonate. Let's leave the compensation for later. Respiratory alkalosis. The minute I see respiratory, the problem is with CO2. Alkalosis, does that mean I have a higher pH? Yes, higher pH will lower PCO2. So therefore my renal response would be to decrease bicarbonate. Well, now let's look at the compensation now. Look at this. You don't need to look at what's the problem. If I have a reduction in HCO3, my compensation will be a reduction in PCO2. If I have an increase in HCO3, my compensation will be an increase in PCO2. If I have an increase in PCO2, my compensation will be an increase in bicarbonate. If I have a reduction in PCO2 and I have respiratory alkalosis, my compensation will be. Now, what do you notice about the compensation and the original problem? They're always in the same direction. And that's always true for simple acid-base problems. If you have a simple, now I underline simple, then you can have a complex acid-base problem where you might have metabolic alkalosis or metabolic or respiratory acidosis both together. But if I have a simple acid-base imbalance, يعني metabolic acidosis or metabolic alkalosis, respiratory acidosis, respiratory alkalosis, just simple acid-base disorder, always the problem with compensation is in the same direction. Okay? Is that clear to everybody? Yes?
How is alkalosis and CO3 and PCO2 is
How is what?
How is alkalosis
Alkalosis? Which one?
and respiratory alkalosis and HC?
Respiratory alkalosis, do we have low PCO2 or high PCO2? Low PCO2. What I'm saying the renal response is to decrease bicarbonate. Remember, this will be the concentration of bicarbonate in my plasma. Again, what you need to remember is the problem, okay, and the compensation are always in the same direction for simple acid-base problem. Now, why is that? So again, respiratory acidosis immediately it's low pH. Respiratory, immediately the problem is with CO2, so therefore immediately when I see high PCO2, I immediately put for the compensation high HCO3 in the plasma. Respiratory alkalosis is that high pH? Yes, respiratory, that means low PCO2. Immediately I know ultimately I will have less bicarbonate in the plasma. Metabolic acidosis, the minute I see metabolic, I know my HCO3 is low. My pH, of course, is lower than normal, and I have acidosis. The respiratory response is a decrease in PCO2. Does that mean hyperventilation? Yeah, hyperventilation. Metabolic alkalosis. Metabolic, that means increase in bicarbonate. Alkalosis, that means an increase in pH. And my respiratory response is an increase in PCO2, which means hypoventilation. Now, why are these always going in the same direction? Well, this is why. طبعا you can think about it, but you can go through the process of seeing what is the kidney going to do in response to acidosis or alkalosis. Or there is a mathematical way you can go about it. You have a question, يا شباب ولا بس تسألوا بعض? You can also determine that mathematically. The reason for that is this Henderson-Hasselbalch equation. I don't know if you've seen that before. Have you seen this?
Yes.
Okay. Henderson-Hasselbalch equation defines my pH. pH is equal to 6.1 plus log to the base 10 of the concentration of bicarbonate in the arterial blood over 0.03 times the PCO2, again in the arterial blood. Now, so this is equal to 6.1 plus log of bicarbonate in the plasma is 24 milliequivalents per liter, 0.03 is 0.03. PCO2 in the arterial blood is 40 millimeters of mercury. So this times this is equal to 1.2. 24 over 1.2 is how much? It's 20. So log to the base 10 of 20 is 1.3. This is a constant. I can't do anything about this. So 6.1 plus 1.3 gives me a normal pH of 7.4. Okay. Now, let's say I have a clinical problem where I have alkalosis. Okay, let's say it's metabolic alkalosis. Just pick one at random. Metabolic alkalosis, does that mean I have an increase in HCO3?
Yes.
So what's going to be my pH now if I have this 24 is not 24, it's 25 or 26 or 27. So I'll have a pH of So if I want to correct the problem, again, we're talking mathematically, but you can gain a lot from knowing a little math. If I want to correct the problem, all what I'm trying to do is bring this number back to 1.3. That's it. And remember, I don't care what I do, as long as I bring this number back to 1.3, I will have fixed the problem, and then my pH will be 7.4, right? If this goes up, there is absolutely no way you can bring this number down to 1.3, except if you increase PCO2. Mathematically, it's impossible. So therefore, the two will go with each other. Let me take another example. Let's say respiratory acidosis. Respiratory acidosis, let's think about that. Do I have higher levels of PCO2?
Yes.
Respiratory acidosis, so higher levels of PCO2. So what is this going to be? See, I'm dividing this by a bigger number, right? So am I going to have 1.3 here?
No.
No, it's going to be less than 1.3, maybe 1. 6 plus 1, 6.1 plus 1 is how much? 7.1. There is absolutely no way I can bring this number back to 1.3 except if I increase bicarbonate. So you mathematically, you don't need to know anything about medicine. If you know a little math, you will be able to determine that both the problem and the compensation will be in the same direction for any simple acid-base problem. Is that clear? Okay. So again, it's your, if you cannot remember this, you remember the Henderson-Hasselbalch equation. You really can from that determine what is the problem and how do I compensate for it. And again, we're talking about simple acid-base balances or acid-base problems, often simple acid-base problems. Then you can have a problem that's kind of complex. Okay, so what did we say are the three different systems that help me neutralize H+? Body fluids, respiratory system, or renal system. This is the renal block. The others we have already talked about. Respiration, we talked about it when we took the cardiovascular block or pulmonary block. Now we will focus on the renal block, but we will mention the body fluid buffers. What is that? That's mainly bicarbonate. Okay, we have a lot of bicarbonate in our body fluids. So a weak acid, this is bicarbonate, is a weak, it forms H2CO3, which we define as a weak acid. And it also, this bicarbonate buffer system consists of, two ingredients, a weak acid, a weak base, or a bicarbonate salt, often, such as sodium bicarbonate. So now, if you have, this bicarbonate system, it's a weak, H2CO3, we said it's a weak acid, so it does not dissociate very strongly, it dissociates weakly, but so therefore it does not dissociate, so therefore I'm not going to have high levels of H+. However, if I have if I have very strong acids such as HCl, right, that dissociates into H+, plus chloride, so therefore then this H+ that came from the hydrochloric acid will react with bicarbonate to give me H2CO3, which ultimately can dissociate into CO2 plus H2O. So now I had originally a strong acid that came from hydrochloric acid. Now I converted it to a weak acid, and further even to carbon dioxide plus water. The carbon dioxide can be expired. So therefore I replaced a very strong acid with a weaker acid, or even CO2 that can be expired to the outside. So now what happens, the opposite happens if I have a strong base, okay, such as sodium hydroxide. Sodium hydroxide, it can be buffered by bicarbonate. If you add H2CO3 again, which is bicarbonate, you will get sodium bicarbonate plus H2O. So you replaced a very strong base which is the hydroxyl ion. It combined with H2CO3 to give me really a very weak base instead of the very strong base that I had, which is the NaOH. Again, so this body fluid buffers, they practically can take care of any H plus that I have in my body. Now, we also have phosphate buffer. Remember when we talked about phosphate, we said it's usually in the form of HPO4 or H2PO4. And what determines how much I'm going to have of HPO4 versus H2PO4 was the pH. If I have very high pH, and very low pH, and a higher concentration of H+, a lot of the H+ will react with HPO4 to give me H2PO4. So this is, okay. So the phosphate buffer system is not as important extracellularly as it is intracellularly. And the reason for that is because if you remember the very famous slide that we have, outside the cell I have only 4 milliequivalents per liter of phosphate. So it's not very important extracellular buffer. However, look at how much is the concentration of phosphate inside the cell. 75 milliequivalents. So I have a lot of phosphate inside the cell. It can play a significant role inside the cell while it's a binary buffer outside the cell, and the concentration is not very high. Okay, well, so what about the renal tubular fluid? Is phosphate an important buffer in the renal tubular fluid? I can tell you it is, because as I filter, phosphate is filtered. We said it's controlled by transport maximum, but I can tell you by the end of the collecting ducts, by the end, as I get to the distal tubule, because I reabsorbed a lot of water, the concentration of phosphate will be very high in the tubular fluid. So therefore it becomes an important tubular buffer. So it's important intracellular buffer. It's also important as a tubular fluid buffer. The main elements, like we said in the phosphate buffer, is H2PO4 or HPO4. What determines how much I'm going to have of this versus this is again pH. If I have a lot of H+, and very low pH, HPO4 will react with H+ to give me H2PO4. And again, under normal circumstances, the concentrations of HPO4 versus H2PO4 is about that much, but again, the amount of H2PO4 versus HPO4 I'm going to have will depend upon the concentration of H+ that I have in the body fluids, or again, that simply means the concentration of H+. If I have a lot of H+, a lot of HPO4 will be converted to H2PO4, and this way, remember now, the ultimate objective is to get rid of H+, or to neutralize H+. Lano H+ is the only thing that's in the definition of pH. That's what determines pH. All these other things, if I convert H+ to something else, then I'm fine. That will keep the pH control. Okay, so the phosphate buffer system, how does it work? A strong acid can react with this HPO4, the H+ from a very strong acid, and it associates quickly and vigorously. It can react with HPO4 to give me H2PO4 and a salt. And again, the opposite happens if I have a strong acid, a strong base, often like NaOH, then it will react with H2PO4 to give me HPO4. In this case, I will have a lot less H+. So now, instead of having this very strong base, I convert it into a weak base, which is Na2HPO4. Phosphate buffer system, again, like we said, it's not very important extracellularly, but it's very important intracellularly, and the reason for, and in the tubular fluid, the reason why it's important intracellularly, again, because the concentration of phosphate is extremely high as compared to what it is outside. The concentration of phosphate inside is 75 milliequivalents as compared to 4 milliequivalents outside. Not only that, but it's also an important buffer in the tubular fluid. The reason for that, because as I reach the distal part of the nephron, the concentration of phosphate in the tubular fluid is high. Not only that, but the tubular fluid has a tendency to be acidic, So its pH is less than 7.4. This, the operating range for this phosphate buffer is a pK of 6.8, which is less than 7.4. So this buffer becomes more effective in the tubular fluid, like the tubular fluid is kind of acidic, so it has it has a pH that is closer to the dissociation constant of the phosphate buffer. Okay, I can see you, some of you are starting to go to sleep, so let me stop here. Inshallah, we'll continue with this tomorrow. Thank you very much.